We've been talking about basic backgrounds of mathematics for machine learning. So this chapter covers probability and statistics for machine learning. It's very brief. So in this chapter, we're going to follow this outline. So we'll talk about some basic stuff about the probability and statistics, and we'll talk about some equations to calculate expectation and variance and moment. And we'll talk about some rules and the properties of probability. Next, we'll talk about Bayes rules, which is really important, and the Gaussian distribution, which is another, and some other distributions too. So before talk about the equations and technical definitions, let's take this example as a warm-up. So we have 5 apples and 7 oranges in red box and blue box. Then let's assume that the probability to pick the red box is 0.3. Okay, then we have a couple of distributions here. So to choose a red box is 0.3, and to choose the blue box is the 0.7. And in the red box, the distribution of the fruit is like this. We have 2 apples out of 7, and we have 5 oranges out of 7. And in blue box, we have 3 apples out of 5 and 2 oranges out of 5. Okay, so this one is one distribution, and this one is another distribution, and this one is also one distribution. And then the question is, what is the probability to pick an apple? Then we have to choose one box, and then we have to choose one apple in the box. So first, if we choose the red box, the probability is 0.3, and then we have to multiply this one because we have only 2 apples in the box. And then there is one more box. Okay, so if we choose the blue box with a probability of 0.7, and then we have to multiply this number because we have 3 apples out of 5. So far it's easy and somehow it's intuitive. Then there is the next question. Now we have picked one fruit. Maybe it could be an apple from the red box. Then what is the probability to pick an apple from this? Then this number should change, right? So 1/6, because after picking the first apple, then we have 6 fruits and only 1 is the apple. Okay, then we change the distribution here. And if the first pick was orange from, let's say, from this one, then this number should change. Okay, so 3/4. Okay, so by this example, what I'm saying is that after choosing the first fruit, if we don't put it back to the original box where it actually came from, then distribution changes. Okay, but if we return the fruit back to the original box, then we don't change the distribution, so we have the same kind of distribution. That's what is identically distributed. Basically, they have the same kind of distribution. Okay, and then if we don't replace, then when we pick the next fruit, the probability of the next pick would depend on the first pick. Okay, so they are not independent. But if we replace the first pick to the original box, then no matter what kind of fruit we choose for the first time, when we pick the second fruit, it doesn't change. It doesn't matter. So they have nothing to do with each other. So they are independent. So we have independent, identically distributed concept many times in machine learning. We usually we assume this, okay, when we use samples from the data set. But you have to make sure that the problem is actually IID. Otherwise, if we apply machine learning algorithms to the data set, where IID was not guaranteed, then you will have some problem. Okay, so in the previous slide, but the question was really intuitive, okay? But sometimes it's not intuitive. So let's take this example, Simpson's paradox. So we have two tables, but let's just focus on the kidney stone treatment. Okay, so in this table, we have stone size, small stone and large stone. And we have two different treatment, A and B. So we have two cases. For a small stone, if we calculate the success rate of the treatment A, then that is 93. But for treatment B, it is 87%. So which means for small stone, treatment A is more accurate. So we have to apply the treatment A, right? And for large stone, if we apply treatment A, then the 73 is the success rate. But treatment B has 69. So in both cases, whether the stone is small or large, if we apply a treatment A, the success rate is higher than treatment B. Then if we sum them up, so if we calculate both cases at the same time, so we add 83 to 63, then we have 350, and we added these two numbers, then we got 273. And we do the same thing for treatment B. Then look at this number. Success rate for treatment A is 78% and success rate for treatment B is 83%. So individually, treatment A was better than treatment B for small stone and for large stone. But if we calculate all of them together, then treatment B is more accurate, more successful. This is a little awkward. And where's the problem here? The problem is here. Treatment A was applied to the large stone dominantly, and treatment B was applied to the small stone. If we focus on these percentages, then we might get fooled by these percentage numbers. But if we focus on this actual count, okay, then treatment A is for large stone and treatment B is for small stone mainly. And in this cell, the successful rate is 73. And for this cell, success rate is 87. So this one is dominant for treatment B and this one is dominant for treatment A. And treatment A has 73, treatment B has 87. So this one is mainly coming from this one, and this one is mainly coming from this one. So if we combine these two cases, then treatment B is better than treatment A. And the batting average says the same thing basically. Okay, so we had a couple of examples. So now let's talk about the probability and uncertainty. So probability is a number, is defined to be a number assigned to an event, okay, and indicating how likely the event will occur when randomly selected. That's what we did with the apple and orange example. Okay, then the why probability. Why are we talking about the probability? Because the pattern recognition is all about uncertainty, okay, and this uncertainty might be from the system or from the measurement, or it could be from the model itself. And the probability is considered to quantify uncertainty. Okay, so basically when we talk about the probability, it implies that there is uncertainty. And it looks like uncertainty is a bad thing that we have to remove. And we try, but we cannot remove uncertainty 100% most of the time. Okay, but the uncertainty is not just a bad thing. Sometimes uncertainty can make the model simpler, which is good. Okay, so we sometimes we prefer a simple uncertain model rather than a complex certain one. Even when the modeling the true deterministic rule is possible. Even when we can make a perfect model, sometimes we prefer simpler one. So here is an example. When we describe a baby, okay, so most of the time the baby is lovely. Okay, but to be exact, we have to describe this most of the time like this. The baby is lovely except when she is sleepy or hungry, or we have to describe all the details here. But we prefer this statement rather than this one because this one is more simple and more efficient to deliver the message, right? So sometimes we don't need these details. Okay, so even though describing the details is possible, but we don't like it because the simpler model is better with some amount of uncertainty. Okay, now we have some idea about the probability, and then now I want to talk about the probability and statistics. Okay, so basically, probability is a mathematical term, and statistics is a empirical term. Okay, so probability measures the likelihood that events will occur, as you know, and the distribution provides the probability of event. Okay, and the primaries can describe the population. So, for example, if we have a dice, then 1 over 6, 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 1 over 6. This is the distribution. Okay, and then this is the parameter. Okay, and if we have a Gaussian distribution, we're going to talk about the Gaussian distribution later in detail, but I think you already know somehow. Okay, so in the Gaussian distribution, we have to define the mean and variance. And the mean and variance are the parameters to define the distribution. And usually the parameters are unknown. And statistics is a science of collecting and analyzing numerical data in large quantities. So when we talk about the data, then pretty much we are going to talk about the statistics. And it can be computed from the sample data. And we often use the statistics to estimate unknown parameters. There is a connection. So when we talk about the probability and there is a distribution and the distribution can be modeled, and in the distribution we have to have some parameters like mean and variance. But these parameters are unknown. But when we have a data samples, then we can estimate these parameters. For example, we can calculate sample average and the variance for Gaussian parameters. Next terminology is random variable. Okay, random variable is a variable, as the title says, whose possible values are numerical outcomes of a random phenomena. So when we toss a coin, in this example, head and tail, these are the phenomena. Okay, so sometimes we have a tail, sometimes we have a head. Okay, but these are random variables value. So when we have a tail, then the random variable's value would be 0. Or for head, it could be a 1. So it is a variable, and at the same time, it is a function. As you can see here, from this, we have a mapping here, like this. It's a measurable function from a set of possible outcomes to measurable space. So this is random variable x, and this is event or outcome, and this is values for the random variable. Okay. Now let's talk about probability functions. Okay, for discrete random variables, we can define the probability mass function like this. For a dice, then we can have 1 over 6 for all the cases. Okay, and otherwise, if x is out of this range, then the probability is 0. When we toss a coin, we have only head and tail. Okay, nothing else. For a dice, we have only 6 numbers. The probability for 7 is 0 because we don't have 7 in the dice. And for a continuous random variable, we can define probability density function, which is a continuous function. Okay. And cumulative distribution function CDF is actually integral of the PDF, and the PDF is derivative of CDF. Okay. And there are 2 constraints for probability. This one. So as long as a function satisfies these 2 constraints, then it can be interpreted as a probability. The first one, the probability should be positive, or at least it should be equal to 0. So which means it cannot be a negative number. And if we take an integral, then it should be exactly 1. So as long as the function satisfies these 2 constraints, then that function can be considered as a probability. And the next one is expectations. So for discrete value, we can actually use a summation. Okay, and this is a function of f, and this is probability. So when we calculate the expectation of this function, then we have to multiply the probability and the function value here for all x. Okay, and for a continuous variable, we need the integral instead of this summation. Sometimes when we derive some equations, we focus on the continuous case, because for a discrete case, if we just change the equations from integral to summation, basically it says the same thing. And for the conditional expectations, we have f of x and we have a conditional probability. So we'll talk about the conditional probability later. And for continuous x, basically it's the same thing as before. We just use integral here. Okay, so far we have been talking about mathematical notations. Okay, and this expectation can be approximated by average sum. This is all about the statistics. Okay, so we have n data samples, and we just calculate the function f with all the samples, and then we just take an average. That's the approximated expectation. And for the continuous ones, we don't have integral here because we have only n data samples. So in this case, this one and this one are exactly the same. So this one is not expectation. This one is just approximation based on average. And these are expectations. Okay, so these are just ideal numbers we cannot get. This one, yes, we can calculate based on the samples. Okay, and expectation is linear. Linear means if we multiply some constant and if we add, then if we calculate expectation, that is it can be rewritten in this way. So a is out of this expectation, b is out of this expectation, and sum is here. And then we know how to calculate the expectation. Now we can calculate the variance and the covariance. So given this one random variable or the function of this random variable, we can calculate the variance in this way. This is the definition of variance. So we have expectation, and from x we subtract this expectation, and then we square. So basically this one is basically the same as this one, except this function evaluation. And when we have 2 random variables, then we can calculate the covariance. Okay, so instead of having square, we have x minus expectation of x, y minus expectation of y, and then we multiply these 2 terms in this expectation. If you look at this equation, then it looks similar, but instead of having this square, we have xy. Instead of having squared, we have expectation of x and expectation of y. And if the random variables are vectors, then we can have this matrix. So far we have talked about the expectation and the variance. And in the expectation we don't have a square, and the variance we have a square. Okay, so these are the first order statistics and second order statistics. And we can extend these statistics to higher order. So we can think of skewness, which is the third order statistics. So we have to the power of 3. And kurtosis, we have to the power of 4. Okay, so we can imagine some higher order statistics, but I never used the higher order statistics rather than just 4. You know the meaning of this mean and variance. Okay, so mean is the location of the distribution, the center of this mass, and the variance is about the spreadness. Okay, how spread the distribution is, and the skewness is about the skewness. So in this case, the distribution is skewed to the right side. In this case, skewed to the left side. And the kurtosis is about how sharp the distribution is. So basically these moments, the statistics describes the shape of the distribution.